when we're now in our previous work that I just took a picture of. So what the? How could I have lost that already? But I did. Oh, here it is. Our previous work, we found out that for now, not for the problem you're working on, but just for the model, just for modeling. When I said, all right, so V naught y is equal to 12.5 meters per second. So what would the final velocity be of the center of mass coming down? Okay, what goes up must come down. Minus 12.5, neglecting air resistance. Now, actually in the Wired article, it's really for it's really geared more towards engineers and physics majors and people like that to read, because he really gets into the weeds of some crazy equations that are straightforward algebra, but still a little hairy. But you can skip over those because he's a good writer. That article I gave you the link to, he's a really good writer and science writer, and so you can kind of follow his argument, and what he's looking at is, what about the air density and the dryness and the humidity of Mexico City? Did that make a difference? And it actually wound up making a difference, just like home runs hitting the ball at Coors Field in Denver does. But because Mexico City is even higher than Denver. I mean, it's like at 9,000 feet or 8,000 feet or something like it. It's crazy, whatever its altitude is. But anyway, getting back to this, V naught y is 12.5 meters per, and so V final y is negative 12.5 meters per second. And so we know that the acceleration is negative 9.8 meters per second squared, and we've got that formula to help us find the time, where we know that the V final y is equal to V naught y minus 9.8 times t. So you've got all these answers, and you can do that algebra probably pretty straightforward, right? So just be careful. Remember, this guy's negative, and you're going to divide by a negative, so your time's going to come out to be positive. Should work for you out here.